Ladies and gentlemen, let's continue with Chapter 9 on natural convection. With the previous lecture, we looked at paragraph 9.1 out of the textbook of Cengel and Ghajar on the physical mechanism of natural convection. Paragraph 9.1, 9.2 was the equation of motion and the Grashof number. And thirdly, natural convection over surfaces. Different surfaces, and specifically the table in your textbook, I cannot remember the number, I think table 9.1 or something like that. And in that table there are a few geometries. There's a vertical plate, horizontal plate, a cylinder and a sphere, and a few basic surfaces which are available. Okay, now what I would like to do is just to, for clarification purposes, I'm going to do another example, and that's going to be example 9.2. But before I do that, I want to remind you again that convection always, if we think of the fundamentals of convection, then the Nusselt number, that is the thing that we need if we have a convection problem, because we need the heat transfer coefficient. But the Nusselt number is always a function of the Reynolds number, Prandtl number, and the Grashof number. That is as easy you can make it. Now, with our first few chapters on external convection and internal convection, we have first neglected this term. And the problem was driven by the Reynolds number, by flow over it. Now in chapter 9, what we're now going to do is, this one is going to be extremely small. And this one is going to be the one that actually forces or drives the problem. At the end of this chapter, we are going to combine these two and put them together. Okay, so we're still on that path of getting to the point where we are going to connect those two. And all those relationships, Nusselt number is a function of Reynolds, Prandtl, and Grashof. The results are available in graphs, tables, in empirical equations. You have to go and look for it, and you have to look at the fine print very carefully. What you have in the textbook are just some of the important information that has been summarized. So if you're going to in industry specialize on certain aspects of it, this will be a good place to start. But that is not the final in terms of the literature that is available. You will have to go back and you will have to go and get the more detailed literature, and in many cases refine what you see in the textbook. So, as the example of, again, flat plate, and just showing to you the influence of orientation, let's look at the case of a flat plate where there are three possibilities for the flat plate. The first one is the flat plate in a vertical up position. Okay, so that would be configuration 1, is vertical up. The second one is the heated surface facing up. And the third one is the heated surface is facing down. So, just to clarify it, what we're going to do is let's select one of the surfaces, maybe that one. There's the insulation material. So this surface is being heated, and in this case, let's put the insulation material here at the bottom, and in the third case, let's do it like that. And this surface temperature, that surface temperature Ts,
There's Ts, and there's Ts. And Ts, for all cases, is 100 degrees Celsius. And this plate is an environment, so that's the environment T infinite and T infinite. Okay, and T infinite is at 20 degrees Celsius. So, any of you who would like to make an estimate of from which one of these plates will the heat transfer rate be the highest? Everyone, all three of them, surface temperatures at 100. So they've got the same driving force from 20 to 100. There's an 80 degrees delta T. Okay. So which one do you think will be will have the highest heat transfer rate? Second one. Okay. Well, let's see. So let's look at the case. Well, why the second one? Anybody a reason except for guessing? Anybody would like to give me a reason? Yep.
Due to density changes with the air molecules heat up, the density goes down and the convection causes larger density cooled air comes down.
Okay, so his explanation is the heating would cause the density of the air particles to decrease, the buoyancy forces will increase and it will flow up. It is correct, but that will happen with all three of them, isn't it? So which one would be the highest and why? You're on the right path, just think of the thermal boundary layer. Okay, now in one of those cases, the thermal boundary layer is not limited. In this case, we know that the thermal boundary layer is going to develop like that. Okay. In this case, there's actually not going to be a thermal boundary layer, while in this case, the thermal boundary layer is going to be trapped underneath. And the heat transfer coefficient is always directly proportional to 1 divided by the thermal boundary layer. So the thinner the thermal boundary layer, the higher the heat transfer coefficient will be. Okay, so that's the reason. So let's start with the vertical case. The vertical case is firstly, we need TF, the properties. Well, let's first just go and look at the table. If you look at the table, Cameron, if you could just look at the table for us. There's the table in terms of the flat plate, and there you can see it in a vertical position. And there you can see the range of the Rayleigh number. And you can see that Nusselt number is a function of the Rayleigh number, you see? And there's also the Prandtl number. Now the Prandtl number is always at what temperature? Okay. And the Rayleigh number, there's also a property that we need to get at a certain temperature. Now what temperature do we use? We use the film temperature. So the film temperature is the average of the surface temperature plus the environment temperature divided by 2. So in this case it is 100 plus 20 divided by 2. So our film temperature is 60 degrees Celsius, and that is the temperature where we have to go and get all the properties. Right. Now at that temperature we can get the properties of the thermal conductivity K, which is equal to 0.2808 watts per meter Kelvin. The Prandtl number is equal to 0.7199. The kinematic viscosity is equal to 1.92 multiplied by 10 to the minus 5 square meters per second, and beta is 1 divided by the film temperature, if it's an ideal gas. So in the tables, I cannot remember which table it is, I think table A5 or A9 for air,
At that temperature, you will see there's no beta value. So if you don't have that, and you can make a good assumption of the fact that it is an ideal gas, you can say it is 1 divided by TF. Okay, so it is 1 divided by 273 plus 60. That would be the value of beta. Right, so here are the properties, and if you look at the equation, you'll see you need the Rayleigh number, and you can calculate the Rayleigh number directly. I personally always prefer to first calculate the Grashof number, just because it gives you one less term in the Grashof number to calculate. And the less terms there are, the smaller your chances of making any errors. So the Grashof number is equal to G multiplied by beta Ts minus T infinite multiplied by L y to the in the third direction, Ly, and divided by the kinematic viscosity. Oh goodness, microphone. Okay, thanks. Thanks, Tamara. Okay, so if you look at that, the Ly, I've just put in the Ly to indicate we are going to refer to that length there, that length Ly, and we have two lengths here, and I specifically did that, but I forgot to show it to you. So we've got a length Ly, which is 0.9 meters, and a length in the Z direction, which is equal to 0.7 meters. So that's the dimension of the plate. Okay. And if we look at the sketch, we can see it is in the upward direction. Do you see? 900 millimeters direction. So that is why I'm using the Ly there, just for clarification. Right, so if we go and calculate it, G is equal to 9.81 multiplied by beta, 1 divided by 273 plus 60, multiplied by the temperature difference, 100 minus 20, multiplied by the length is 900 meters, 0.9 to the third, divided by the kinematic viscosity, the dynamic viscosity, 1.92, multiplied by 10 to the minus 5, and remember the square, and that would give us a Grashof number of 2.192 multiplied by 10 to the 9. Okay, is that clear to everybody? Right. Now, the Rayleigh number is equal to the Grashof number multiplied by the Prandtl number. I've just now calculated the Grashof number. The Prandtl number is given as 0.7199. So you can see that we can go and calculate the Rayleigh number as 1.578 multiplied by 10 to the 9. Okay? And now we can calculate the Nusselt number. You see the Nusselt number, now we've got three possibilities in terms of the Rayleigh number range. The Rayleigh number is about 1.6 multiplied by 10 to the 9. So we can not really use the first equation, but it's borderline for the second equation, sort of in between. But if we want to be more accurate, we can use the last one, the long equation. Okay. So that gives us then the equation for the Nusselt number is equal to 0.825 plus all those terms. I'm not even going to write it down. Okay, you can see it there in the overhead. Tamron, if you can just go there quickly again. So it is equal to 0.825 plus 0.387 Rayleigh based on the length to the 6 divided by 1 plus 0.492 divided by the Prandtl to the 9 divided by 16 to the power of 8 divided by 27 and everything to the power of 2. You see the long equation? Okay. And everything is known. You see? Nothing unknown in the equation. So if you go and calculate it, then it gives you the Nusselt number as 141.8. 141.8. Now what does the Nusselt number mean again? The Nusselt number tells us how much is the heat enhanced in comparison with conduction heat transfer. Because with conduction heat transfer, the Nusselt number will be 1. So it means that because of natural convection, the heat transfer will be 141, almost 142 times larger than conduction. If you take this plate into outer space where gravity is 0, there is no natural convection, and then the Nusselt number would be 1. Heat transfer will be by conduction only. Okay, that is what it means. So Nusselt number is equal to the heat transfer coefficient multiplied by characteristic length divided by K. Now, which characteristic length? Of course, the characteristic length that we have chosen for the Grashof number, and actually we should put in Grashof L there, because that is in the equation, it says Grashof L, okay, based on the characteristic length, and that is equal to the Nusselt number, and that is equal to 141.8. So the Nusselt number is equal to 141.8, is equal to the heat transfer coefficient multiplied by the length divided by the thermal conductivity, 0.2808, and that gives us the heat transfer coefficient as 5.687 watts per square meter degree Celsius. When you calculate the heat transfer coefficient, always ask yourself, does it make sense? In this case, yes. Natural heat transfer convection, heat transfer coefficients up to about 10, 20, very low values. Okay, not in tens of thousands. Boiling, condensation, evaporation. Then you will have values like that. Right, now that we've got that, we can calculate the convection heat transfer, and the convection heat transfer is equal to the heat transfer coefficient multiplied by the surface area multiplied by Ts minus T infinite. Heat transfer coefficient is equal to 5.687. That's very simple, 5.687. The surface area is 0.9 multiplied by 0.7. And the temperature difference is 100 minus 20. And that will give us a heat transfer rate of 286.6 watts. Is that the total heat transfer rate from the plate? Answer is no, because with the previous lecture, I've showed to you how important radiation heat transfer is, especially with these types of problems. We do not have time to go and calculate it, but if you go and calculate the radiation heat transfer as the emissivity multiplied by the Stefan Boltzmann constant multiplied by the surface area Ts minus T infinite to the fourth, remember it's in Kelvin, then you'll see that the radiation heat transfer rate is equal to 428.2 watts. That would be with an emissivity of 1. Will the emissivity be 1? Well, it will depend on the surface of the plate. Okay, and that you're going to do in 2 later chapters, and we will get to that later. But if you assume it is equal to 1. So you can see that the radiation heat transfer is actually much larger than that of the natural convection. And obviously the total heat transfer rate will then be 714.8 watts. Right, so that would be for the plate in a vertical position.
Let's look at the second configuration now. With the second one, we have the flat plate like that, 0.9 meters by 0.7. Here's the flat plate, like that, and it's insulated here at the bottom. And that surface there is 100 degrees Celsius, while the environment temperature is the same, it is 20 degrees Celsius. Okay, now Tamron, if you can look at this for me. Let's see. Right, there in your table, there's the case for the horizontal plate. And the first one you see is for the hot surface at the top. Okay? And what does it say? It says surface the area A in the perimeter P, the upper surface of a hot plate or lower surface of a cold plate. And there are some equations. Do you see it? To be used. However, is the important one, and that is that small second column, which in many cases you miss. And what does that small second column say? It says, if you calculate the characteristic length, you cannot choose like 0.9 meters in this case. You have to go and calculate it differently. So it's the small print that is important. So for the Grashof equation, which is equal to G, B multiplied by Ts minus T infinite multiplied by the characteristic length to the third divided by the kinematic viscosity. What it now says is that this characteristic length, LC, is equal to the surface area divided by the perimeter of the plate. And the surface area would be equal to 0.9 multiplied by 0.7 divided by 0.9 plus 0.7. Okay? So it's 0.9 plus 0.9, 0.7 plus 0.7, so two times of each. Just the perimeter of a flat plate. And take note, the characteristic length is only 0.1969 meters. So the characteristic length now becomes only about 200 millimeters. Very small. Right, now we can put this back in calculating LC. G stays the same, beta stays the same, the temperature difference the same, and the viscosity the same. So the only thing that changed was the characteristic length. You agree? Okay. And if you now go and calculate the Grashof number, then it is equal to 4.877 multiplied by 10 to the 7. And then the Rayleigh number, which is equal to the Grashof number multiplied by the Prandtl number, is equal to 3.511 multiplied by 10 to the 7th. Look at the available equations, then you can see there are two equations which are available, depending on the value of the Rayleigh number. If it's 10 to the 4 to 10 to the 7, then it's the first equation. Nusselt number is equal to 0.59 Rayleigh to the 4th, you see? And if it's larger, 10 to the 7 to 10 to the 11, it is equal to, Nusselt is equal to not 0.1, but 0.15. Remember, there's a printing error in the textbook. There's at least 2 errors in that table. Okay, does that make sense? Right, so we calculate the Nusselt number now with a simpler equation.
0.15 multiplied by Rayleigh to the third. And there's the Rayleigh. I just need to put it in there, and it gives me a Nusselt number of 48.83. The Nusselt number is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity. The Nusselt number is 48.83. The heat transfer coefficient multiplied by the characteristic length, which is equal to 0.1969, divided by the thermal conductivity, which is equal to 0.2808, and that will give me a heat transfer coefficient of 6.966 watts per square meter degree Celsius. Okay? So let's go and calculate the convection heat transfer rate. It's equal to the heat transfer coefficient multiplied by the surface area multiplied by the temperature difference. The heat transfer coefficient is 6.966. The surface area is 0.9 multiplied by 0.7. I've got the temperature difference, and then I can calculate the convection heat transfer as 351.1 watts. Okay. The radiation heat transfer, cannot forget about it. That's not going to change because it's not being influenced by the heat transfer coefficient. It is only being influenced by the temperature difference if it's the same plate. Okay, so the radiation heat transfer is going to be the same, 428.2 watts, and therefore the total heat transfer rate is equal to 779.3 watts. Okay. So we can see it is higher in the case of the horizontal plate. Does that make sense? Right. The third case is now where this is the plate and all the insulation material is on that side. Let's say that is 900 millimeters by 700 millimeters. And now this surface here is at 100 degrees Celsius, while the environment temperature is at 20 degrees Celsius. Again, for that specific application, go and look what the table says. Okay. So again, if we look at this table, it says the characteristic length, we have to calculate, again, by using the surface area divided by the perimeter. Okay, so LC is equal to the surface area divided by the perimeter, and that would mean that it is not going to change. It is going to stay as 0.1969 meters. You see? The Rayleigh number, or the Grashof number, is also going to stay the same. 4.877 multiplied by 10 to the 7, because nothing changes there. The Rayleigh number is going to be 3.511 multiplied by 10 to the 7th. But now the equation to be used. The equation to be used, well, there's only one. And it says that that equation can be used if the Rayleigh number is between 10 to the 5 and 10 to the 11. So we are lucky. We are in the range. You see? Okay. So the Nusselt number is then equal to 0.27 multiplied by the Rayleigh based on the characteristic length to the quarter. There's a rally. We can do the calculation, and that gives us a Nusselt number of 20.78. Calculations are exactly the same. The characteristic length is exactly the same. It gives us a heat transfer coefficient of 2.965, approximately 3 watts per square meter degree Celsius. And you can now go and calculate the conduction heat transfer as 149.4 watts, and the radiation heat transfer stays the same, 428.2 watts, and that would give us a total heat transfer rate of 577.6 watts. So if we look at the three cases, and we only look at the convection heat transfer rate, then for the vertical plate, the convection was 286.6 watts, like that. For the case where we had the plate like that is the heated surface there at the top. That was case 1, that was case 2. Then the convection heat transfer rate was 351.1 watts. And then the third case was where the heated surface were at the bottom. Heat transfer rate from there. And then the convection heat transfer rate was equal to 149.4 watts. The radiation for each one of them the same, but it clearly illustrates the importance of the thermal boundary layer. This thermal boundary layer, as I've explained at the beginning, it's going to form like that, and it becomes thicker and thicker. And the thicker it becomes, the lower the heat transfer coefficient will be. In this case, the thermal boundary layer is going to break up all the time because of the convection just going up. And in this case, it's going to build up here. You're going to have a thick thermal boundary layer at the bottom. Okay? And that's the reason why the heat transfer rate from that plate would be the highest. Any questions, ladies and gentlemen? Yep.
So what if the rally number is outside that?
Yes, if it's outside, then you have a problem, and then you have to go to literature and get values. Some of you end up in the exam, you know, now you're just outside the range. Now you wonder, what do I do now? Because there's nothing else. If there's nothing else, then you will have to say, you know, I realize this is outside the range. And I realize most probably I've made a calculation error. So I know I shouldn't actually use it, but because there's nothing else, I'm going to use this correlation, then it's fine. Okay. Right, okay. But you should also, something that I should add is that in many cases the ranges, of course, is very important, and especially if you're doing designs where you're competing against others. But many experiments were just conducted in a certain experimental range. And the reasons are you had maybe a pump or you had a fan, and that is what you had. So you did the experiments with the equipment that you had. But maybe if you could have pushed it a little bit more, yes, maybe the equation might still be in range. It's difficult to say. Okay. Right. Okay, now let's continue now with this chapter. What is the important thing of this chapter? And let me just come back to this original equation that we had here. This chapter is all about that, the Grashof number, and then later on the effect of this one also. And you will see that for every geometry there's an equation or a table or a limitation. So it's all about the fine print. So we are not going to go through every possible configuration that you can think of from where we can have natural convection, because the principles are exactly the same. And There are many other geometries, for example, the ones that we're going to do now with fins. Again, which has equations. But what is important now is that you will have to go and work through the textbook. At the end of the chapter, there's about 120 problems. You have to go and work through many of them because it will give you a feeling. The more you practice with it, the better. Don't have the attitude that, yeah, I know it's about the fine print. When I get to the exam, I'll quickly go and read the fine print, and then I will do it as the fine print says. In many cases, it doesn't really work like that. You really need to exercise. Something that I've mentioned with the previous lecture, which is important, is that if you go and look at the equations now in the fine print, for example, the classical case of the flat plate, then there are two possibilities. The one possibility is the one that we've done now, where the surface area of the plate was a constant. Okay. And the result of that would, of course, be that if we measure the temperatures on the plate, and that is approximately the values of the temperature, if we could represent it as straight lines, not as vectors, then that would be the temperature profile. But another case might be the case of a constant heat flux. And you will see there are also equations in your textbook for constant heat flux. So with a constant heat flux, you will have something doing something like that. So the temperature profile would actually increase in that direction. So if you've got a flat plate, why would it be in that direction and not in this direction? Because the thermal boundary layer is going to grow in the upwards direction. So that's the reason for it. Okay. Now, the fine print again will direct you in terms of the equations to be used. And for example, with a constant heat flux case, you need to use that temperature Ts, which is the average temperature halfway through the plate. But if you start with a problem like this, normally the surface temperature and the environment temperature is given, so you can calculate the film temperature. When you're given a problem of a flat plate with a heat flux of 1 kilowatts per square meter, you don't have a surface temperature. So you have a problem getting the film temperature. So as we've discussed previously, you guess one, and you have to go through all the calculations. Then you're going to calculate the temperature there, and then you're going to correct your iteration. Okay. Now, that is something important to remember. But what happens here is that there are now two types of Rayleigh numbers and Grashof numbers which are being introduced. The first one is for the case where we've got a constant surface temperature, and the second one where we've got a constant heat flux. Okay. If we've got a constant surface temperature, we calculate our Rayleigh number as G multiplied by beta, Ts minus T infinite, L to the third, divided by the kinematic viscosity. You can multiply it with the Prandtl number, and that part is, of course, the Grashof number, as we've done up to now. But now what is being introduced here is this Rayleigh number. Okay. This one indicates a constant heat flux case. And because you don't have the delta T, with a little bit of manipulation, you can actually write this thing in terms of constant heat flux. And this equation would be equal to G multiplied by beta, multiplied by the heat flux, multiplied by L to the fourth. So there's an extra dimension that comes out, L to the fourth, divided by K, kinematic viscosity square, multiplied by the Prandtl number. So this becomes our modified Grashof number, again indicating the one with a constant heat flux. So when you get to the tables or the equations, you will see two different types of them. So if you wonder where this comes from, it's the constant heat flux cases. Okay, now with the information in your textbook, let's suppose we say write this exam now, let's write an exam. Okay. And I give you a case where you've got two flat plates like this, which forms a channel. Forms a channel. Okay, and let's suppose that direction is relatively large. Okay, so Here's the beginning of the channel, and there it goes like that. With the equations available, without going through with a textbook, just with that table, do you think there's a way out for you in terms of using those equations? You think you can get out of it? I think yes, it is. There's a possibility. Remember that obviously it's going to depend on how far the two plates are from each other, because this is actually two flat plates. And what they're going to do is they're going to have the thermal boundary layer that's going to grow up to that point there. And from there on, we know we've got fully developed flow. Okay. But in this region here, this boundary layer is not being influenced by the other boundary layer. So this is a flat plate situation. You see? It's a flat plate. Just by considering a flat plate, you can get the heat transfer rate from this one and from that one, and you can do your calculations. So remember, small things like this is very important. Okay, now the next part of the work is about fins. If we can just look at, if I can get out of here quickly, let's see if I can show you a better sketch. Okay. There are many applications of convection heat transfer from electronic components. And usually you will see fins like that, which are called heat sinks. So this is where the heat is being released to the air, and they are very robust because in many cases there's no fans. These days, more and more of the electronic components come out with fans because the heat that is being dissipated is just so much they can't get rid of it, so it has become a huge problem. But in general, this is also an application of a flat plate. You agree? Okay. But it now depends on the length L. If the length becomes very large, okay, then a significant part might be fully developed. So again, it depends on the length. Now if you look in the textbook, again, you will see now that there are now many equations available. And again, they are divided in the constant wall cases and the constant heat flux cases. So for example, for the case where T is a constant, just as an example, okay, for them, the Nusselt number is then given as heat transfer coefficient multiplied by S divided by K. Cameron, can you quickly look there on the slide for us? Where's S? Oh, you can't see it, so let me make it a little bit smaller. There you can see. So you see S is the distance between the fins. So the heat transfer coefficient is being written as the distance between the fins, not the length of the flat plate that we have here on the side. And that equation looks something like that, 576 divided by the Rayleigh, take note, based on S, the fin spacing, multiplied by S divided by L to the square plus something like 2.873 divided by the Rayleigh based on the fin spacing, multiplied by S divided by L to the 0.5 and everything to the minus 0.5. So that is typically how the equation looks like to get the Nusselt number. Okay. Now what is the problem when you design these types of equipment? The challenge is to get the optimum spacing between the fins. Okay. Because the more fins you put in, the more surface area you will get. And the more surface area you get, the more heat transfer you can get. Okay? So the challenge is normally getting in more and more fins. But somehow, at a stage, you get to this length where the fins become so small to each other that most of the flow is fully developed and the two thermal boundary layers touch, and when it happens, the heat transfer coefficient decreases. So you've got that optimum that needs to be taken into consideration. And the optimum has been solved by Avi Bar Cohen. And that is equal to 2.714 multiplied by L divided by Rayleigh to the L to the 0.25. I see a Rayleigh L here. I cannot now remember if it's an L or an S. Okay. Is it an L? If it is an L, it is based on the length L in the dimensions. Okay, so just take careful note of this. Okay. If you now have solved this, and obviously you get that from experiments, and you put this back into that equation, then you can solve the optimum Nusselt number for that case. And that would only be about 1.307. 1.307. Now I think many of you would say, but this is really a little bit disappointing, isn't it? Because the heat transfer enhancement is just 30% in comparison with conduction. However, what is important is remember the heat transfer coefficient that you're going to get from there. You're going to use it in an equation where the heat transfer rate is equal to, yes, that heat transfer coefficient, but multiplied by the surface area. And there's so many of these flat plates, of these fins. So you win with the increasing area. Not so much, maybe with the heat transfer coefficient. Okay. So with that work, for example, you can go and get the heat transfer coefficient for fins, and the fact that I don't do an example about it doesn't mean it is not important. Again, it comes back to the principle of the Nusselt number as a function of Reynolds, Prandtl, Grashof. We cannot do every possible geometry on Earth. There's one more geometry that is important, however, that I would just like to say a few things about, and that is for enclosures. And that would be paragraph 9.5. And the classical example that is being used is, for example, an enclosure like this. Okay, ladies and gentlemen, could I ask you to quiet down, please? Okay. The classical example is something like this. Any of you see some applications in this? Where? Somebody said something, but I cannot hear.
Heat exchangers, double glazed glass.
Yes, glass, especially in the heating, ventilation, and air conditioning industry. Glass is one of your biggest challenges in a building. The heat transfer losses, most or a significant part of it is through glass. In South Africa, we do not really have such extreme challenges, but in Europe and other climates where you've got temperatures on the outside of -20 and -80 and stuff like that, you really need to keep the heat inside. Okay. So normally, in many cases, you've got two glass panels there, and inside that, you also have circulation. And again, the angle would determine how much circulation you have, and there are lots of equations in your textbook. We are not going to go through all of them. But this, if you go through it, reduces to, at the end, something where they get the overall heat transfer coefficient, okay, the U. And many of you that have worked, maybe that did some holiday work in the air conditioning and ventilation industry, would have seen that you use your designs with a U factor. Okay. Now what is interesting with that is, of course, for glass, you would like this, obviously the heat transfer coefficient, to get it as low as possible for the natural convection. How can you do that? Well, with this distance, so the distance plays a role, okay, and also the gas inside, or if there's no gas in. So air would have certain properties, argon would have another property, etc. You can put different gases in the glass and you can seal it. So if you look in your textbook, it is now part of the last part of the last part of the chapter, and it is under special categories or special subjects. So we're not going to get to it, but for those of you working in this industry, you can go and read this and it would be a good start to work from. But typically, if you look at single glazing glass, 3 millimeters, then the U factor will be about 10. Okay, the U factor will be about 10. If you look at triple glazing glass with a 12.7 millimeter air space, then the U factor goes down to about 1.19. Or if you use argon inside, then it would go down to 0.8. So from 10 to 0.8. You can decrease the losses by a factor of 10 and more just by using the right types of glass and by sealing them. But you'll see it's a very complicated thing. It depends on the frame and it depends on many factors. All that information is normally available in tables and you can go and take a look at that. Any questions, ladies and gentlemen? Nothing? Thank you very much.